Hey guys, I totally forgot during lecture today that I didn't. I mean, I did finish 7.8, but I don't feel comfortable with just the minimalistic treatment that I left you with for the convergent or the comparison theorem, using the comparison theorem to determine convergence. So I want to give an addendum here, and one of them will be a homework problem, just because I think that homework problem is really neat. But the idea with the comparison theorem is really that if you have two functions, let's say f of x and g of x, and you happen to know for an example that f of x is greater than or equal to g of x and g of x is positive or non-negative is probably the best way to say that, and these are continuous functions. Well, if the integral from a to infinity of f of x dx converges, so tends to some finite number, I'll call capital N, okay, since that is a finite number, and G is positive. G being positive is incredibly important here, or non-negative. Again, the fact that we're requiring G to be greater than or equal to 0 means that the only thing that can happen with the area underneath G is that it will continually grow, or at, at best is that it will stay 0. So this could be G right here, but the fact is the area underneath it, you're never going to subtract an area. In other words, it's never going to do this, go below. It's always going to continue to at least somewhat add an area to it. And that's critically important because I know it's not going to start adding and subtracting values. So therefore, if I know that it's always at worst going to be adding values, but at best going to be adding nothing as time goes on, and I happen to know that f of x converges, the area under f of x, that converges, then I know the area underneath g also has to be contained. Okay, so that would imply the area from a to infinity underneath the curve g also has to be contained. It will likely not approach the same number, but it'll at least be finite and approach some finite number. Again, if the red curve that I'm about to draw, this guy right here, represents f, and g is always below it, but f becomes finite, then g must be finite as well. On the other hand, if the area underneath g, I could use that same exact picture, in fact. If the area underneath g is not finite, and in this case, because they're both positive, what that basically means is that it tends to infinity. And that's just uh, the idea there. Because g is positive, what it's going to do every step of the way is add more area. If that area does not become finite, so in other words, that it's infinite, that implies, because f is above that, that the area underneath f here will also be infinite because f is contained or is greater than g. So the area from a to infinity underneath f of x, g of x is also infinite. Okay. So saying all that, I'm going to go ahead and swoop this up and delete it. Saying all that, where's my delete? There it is. Boom. Let's go ahead and tackle this problem. Let's talk about tactics to start the comparison theorem. So the best tactic, honestly, is to look at the ultimate big boys on the block. So look for, I'll say, look for the largest function. Now this could be somewhat, oh, by the way, that largest function in both the numerator and the denominator. Now this could be somewhat obvious, as in the case that we're looking at here, and then we'll take an example where the case is not so obvious. So the largest function in the numerator is just 1, and then the largest, most bad function in the denominator is e to the x. So that's what I'm going to compare it to. I'm going to compare that fraction, compare to y equals e to the x. So how I personally start doing this is, if I know that the numerator is a constant, I'll just compare denominators. So that'll be this example. I'm going to look at e to the x, and I'll consider e to the x plus x, which is that denominator. I can easily see, since x is going to be positive, that the e to the x plus x is greater than e to the x. Now I'm going to take the reciprocal of both sides, because the fact is I'm not dealing with just x e to the x. I'm dealing with 1 over x plus e to the x. So I'll take the reciprocal of both sides. And when you take reciprocals of inequalities, the inequalities flip. Now, it needs to be said here that 1 over e to the x plus x is actually positive. That's critical for us to be able to use the comparison theorem. And so now I will go ahead and investigate whether or not 1 over e to the x as an integral converges. So we'll go ahead and tackle that. We don't have a theorem or anything that helps us here, so I'll just go ahead and go through the integral from 3 to infinity of 1 over e to the x. dx is the same thing. Remember, we have to convert this to a limit as t goes to infinity of the integral from 3 to t of e to the negative x dx. And now I can run the antiderivative. Maybe I should stack it here. That's the limit as t tends to infinity. The antiderivative is negative e to the negative x, and we're evaluating that from 3 to t. And finally, limit as t goes to infinity of a negative quantity e to the negative t minus e to the negative 3. And as t goes to infinity, e to the negative t tends to 0. So I happen to know that that tends to 0. Let me just write that in there, tends to 0. And so this will just be a positive e to the negative third, which is finite. That's all I care about. I care about the fact that this turns into some finite value. So finite implies it converges. And so if I know that the integral of e to the x converges, then because it's greater than another positive integral 1 over e to the x plus x, I know that from 3 to infinity, that also must converge by the comparison theorem. So this implies that the integral from 3 to infinity of 1 over x plus e to the x dx converges. Now I'm going to steal one from your homework because I think that it's just such a good example. And again, totally flubbed on talking about it in class because I got so excited about moving into chapter 11. So here's the example. Integral from 1 to infinity of x plus 1 over the square root of x to the fourth minus x dx. There's several issues with this, but just taking my advice, my tactic, which is to kind of look for the highest power in the numerator or the biggest bad boy in the numerator, which is going to be x, and the biggest bad boy in the denominator, which is the square root of x to the fourth, I will create a function to compare it to. This doesn't mean that I automatically know that I'll be able to make the comparison, but my goal is to compare to y equals x over the square root of x to the fourth. And of course, that simplifies down. That's just going to be y is equal to x over x squared, or in other words, 1 over x. Now, I happen to know, because the power on that is 1, that if I were to integrate this from 1 to infinity, 1 over x dx, that diverges because power is equal to 1, and that's less than or equal to 1. I mean, the fact is, once the power is less than or equal to 1, we have a theorem that states that integral will diverge. So that's what I'm hoping to build the comparison with is 1 over x. So how do you do that? That's the crux of this whole problem. How do you begin even getting into that? With fractions, I always try to compare denominators. So let me go ahead and set this up to start comparing denominators here. So I'll look at, let's see, probably, yeah, let me just take a look at this denominator here. I'm going to look at the square root of x to the fourth minus x. I'll start with that. And looking at that denominator, that's roughly x squared. But if you think about it, it's actually less than the square root of x to the fourth, which is x squared. I want to get somehow to get that square root out of there. So I've successfully done that. I've said x to the fourth minus x underneath the square root. Well, that's definitely less than, because you're subtracting off x and x is positive, that's definitely less than the square root of x to the fourth. And the square root of x to the fourth is x squared. Okay, now I've ripped off the square root. So that's the ultimate. That square root's just a huge annoyance in this problem. By the way, there are many other ways to do this, but it's kind of my preferred method for me. Okay. Now, if I take a look at where I want to end up, 1 over x, I know I need to take the reciprocal of both sides. Moreover, I also know that I have to get an x plus 1 in that numerator of this bad boy when I flip it over. So let's at least flip it over for right now, and we'll worry about how to get there later on. Okay, so if this inequality is true, which it is, we can then take the reciprocal of each side, and when you do that, the inequality flips. All of a sudden you get a greater than. Now again, keeping my eye on the prize, I want to end up with a 1 over x. That's what I want to end up with. So what I'm going to do is go ahead and multiply both sides by x to cancel out that x squared in the denominator. If I do that, and you could totally do this because x is, again, positive because we're going from 1 to infinity. So when I multiply both sides by x, I get x over root x to the fourth minus x is now greater than, multiplying that by x, you get 1 over x. Now, if you look at that, that is not really exactly our integrand. It's almost, I mean, really, if you look at the integrand, we have almost everything there. We have the square root and we have the x in the numerator. But I have to add 1 to that. That's going to be pretty simple. Remember, we want to showcase that we're comparing it to 1 over x. We happen to know that 1 over x diverges. So if there's something bigger than it, that will also diverge. When I say 1 over x diverges, I really am meaning the integral of 1 over x will diverge if you evaluate it from 1 to infinity. But that's a lot to say. Anyhow, if you agree with me so far that x over the square root of x to the fourth minus x is greater than 1 over x, well then you should also agree that if I add 1 to that numerator, it's just going to get a little bit bigger. That's it. And now that I've increased the size of that numerator, which also, increases the size of that fraction, which still keeps it above 1 over x, I can say, well, the integral of from 1 to infinity of 1 over x dx diverges. We've already explained why. But that implies the integral of 1 to infinity of x plus 1 over the square root of x to the fourth minus x dx must also diverge. Again, diverges, sorry. Again, I should also mention definitely our lowest bound is 0, so that's very important. But yeah, so these are the two that I would love to have done in class. I just totally forgot. It also kind of showcases the tactic to kind of tackle these types of integrals. So anyway, enjoy. I hope that helps out.